Okay, so question number 3 is starting off with talking about the membranes, pressures, and mechanisms that make up negative pressure ventilation. And so we'll go ahead and talk about the layers of the membrane first, and there are 6 layers. So the first layer is the fluid in the alveoli, which is surfactant. The next layer is the alveolar epithelium, which lines the alveoli, which are squamous cells. Next, we have the basement membrane of the alveoli. And then next we have an interstitial space. And we have basement membrane of capillaries. And last we have capillary endothelium that is also made up of squamous cells. So now when thinking about this ventilation, we think about pressure. And a good way to kind of define this is by Boyle's law, which states that pressure is inversely related to volume. So if the volume were to increase, the pressure would go down, and vice versa. If the pressure were to increase, the volume would go down. So P is equal to pressure. K is a constant, and V is equal to volume. So it's this idea of pressure and volume being inversely related that kind of guide the lungs for this certain type of ventilation. So now when thinking about the lungs specifically, we can kind of talk about what happens in the lungs in terms of pressure that causes this to happen. So here, if we have our lungs, we know that there is a atmospheric pressure that is coming down from the outside. That is going to be high, around 160. So I'll just give this a positive value here. And so that means that it'll be higher on the outside and it will be lower here on those negative values. And so what we know is there is a space in between the lungs and the chest cavity. And in between here, what I'm highlighting in blue is called the pleural space. And so this space is what causes this negative pressure to happen. So the lungs naturally want to collapse on themselves. They're elastic and they want to close, but there is a negative pressure that is developed, and so this pleural space that has this negative pressure kind of creates this vacuum that keeps the lungs sucked outside, kind of sticking to the chest cavity, and that is what allows us to have this vacuum and difference in pressure is this pleural space. It kind of is the driving force behind this pressure. So if we take the lung and we zoom in and draw the alveoli of one small and one big, just for an example, the important part about alveoli is this balance of pressure. So if we think about it normally, we see that this alveoli here, we have a smaller one, which is going to have a high pressure, and a bigger one, which will have low pressure. And because pressure wants to go from high to low, normally what would happen is the air would rush from this small one to the big one. And so one of our alveoli would be completely collapse. They would want to collapse. So we have a couple things to prevent this. So in the alveoli, we have this layer of water, which contributes to the surface tension, which is what helps the alveoli from naturally collapsing. And so along to help with this surface tension, we have this material, this protein called surfactant in each alveoli. And so that is what reduces surface tension. But the thing about surfactant is that there is an equal number of surfactant in each alveoli. So because of that, the equal number of surfactant will affect each alveoli different and affect the surface tension more on the smaller alveoli, which will allow a kind of a regulation of air that gets put into each different size of alveoli. And so this is illustrated in the law of Laplace, which is pressure equals 2T over R. And so P is pressure, our T is our surface tension, and our R is our radius of alveoli. So we know that as this surface tension decreases due to this increased amount of surfactant per surface area, that will regulate the pressure between the big and the small alveoli. So because of this surface tension and because of surfactant, the amount of pressure and the amount of air that reaches the alveoli is regulated, and we don't have one alveoli that wants to collapse because of pressure wanting to go from high to low. So a pneumothorax can be defined as air in the pleural cavity. So we know that the pleural space is what leads this idea of our vacuum and our negative pressure. So if we have air in this pleural cavity, then that can be a big problem. So what we know is there's a tension pneumothorax, which is caused by there's a damage to the tissue where air flows in to the pleural space, but it cannot flow out. So we kind of make a one-way valve. And so this built-up pressure in the pleural space can cause problems. It can reduce venous return to the heart and can potentially be life-threatening. So the way to solve this, the way to address this, is by relieving that pressure. So if you are able to make an incision and insert a tube maybe between the ribs to relieve the pressure that is in the pleural cavity until it regulates itself again, that would save someone from the potentially threatening situation of a pneumothorax. Okay, so for the last part of this question, we're going to talk about oxygen and carbon dioxide transport to and from the blood. So I've drawn a picture. Here we have the alveolus here, and in red we have the blood vessel. So what happens is we will have the atmospheric pressure bringing in oxygen here. And so what happens is this oxygen will diffuse into the blood and be part of the plasma and will circulate through the blood. But part of it will also enter into red blood cells. And what we know is in red blood cells is hemoglobin, and we will see our oxygen binding to hemoglobin. And so this combination of oxygen-bound hemoglobin makes up for about 98% of the oxygen that we use, whereas the free-floating oxygen makes up for only about 2% of the oxygens that we use. So as we inhale oxygen, it will diffuse into the bloodstream and then further into the red blood cells to bind to hemoglobin in order to be used throughout the body. In contrast, when talking about carbon dioxide, we'll go ahead and start here with the red blood cell. We know that there are transporters that bring in bicarb into the blood, and so these will combine with hydrogen ions as well as H2O and then they will split into carbon dioxide and water. So go ahead and highlight this carbon dioxide, which will then diffuse out of the red blood cells and go into the bloodstream, and it will then continue to diffuse out into the alveolus and out, and it will be what we exhale. So in addition to this pathway, we also have hemoglobin that will be bound by CO2, which will then cause it to go to its T state, which will release oxygen from the hemoglobin to be used throughout the body. But this is the contrasting cycle of oxygen being transported into the blood and used by hemoglobin, as well as our bicarbonate, allowing for CO2 to be made and then diffused out through the alveolus as well. So here I've inserted a graph that is the oxygen hemoglobin saturation curve. So this kind of describes the amount of oxygen that we have and how readily it binds to hemoglobin, the percent saturation here on the y-axis. So we have this normal curve, and it looks like right here around 75%, we have this turn where there is the oxygen in the tissue at rest. So we know that there is a dangerous zone to be below 75 when you're at rest, which can cause some problems. And so this kind of graphically explains how oxygen binds to hemoglobin and its effectiveness used in our bodies. So there are some changes that can happen and some things that can cause some shifts to this curve. So I'll go ahead and draw a little right shift here. The shift to the right can be explained by things like high levels of CO2, high temperature, and low pH. So if we have someone in an acidosis, respiratory acidosis, we know that this graph will be shift a little bit to the right. And so in contrast, we can also have other shifts that happen to this graph that can be to the left. So drawing this here in blue, we know that these shifts can happen for the opposite reason. So if we have decreased CO2 levels or a decrease in temperature with an increase in our pH or alkalosis, then we will see this shift change. So we will have less oxygen per hemoglobin if we're shifting to the left, which can be clearly seen throughout these different types of circumstances that cause this shift in this graph. So this graph is a good way to be able to see the amount of oxygen that is binding to hemoglobin and can give us clues about what type of state the person is in and what different factors influence these shifts in this graph.